Uno, dos, tres, dos, uno, 3, 2, 1. Esta es una prueba de audio. Probando equipo de audio. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Equipo de audio. 1, 2, 3. 1, 2, 3. Equipo de audio. Probando equipo de audio. 1, 2, 3. Poco.
Hola, buenos días a todos. Vamos a dar comienzo a nuestro segundo día de Foro de Salud y Bienestar. Vamos a comenzar el día de hoy con una conferencia magistral. Tengo el gusto y honor de presentar al doctor profesor Jimmy Bell de la Universidad de Westminster, UK. Voy a hacer la presentación en español, la plática va a ser en inglés, pero bueno, el profesor Jimmy Bell estudió una licenciatura en bioquímica en la Universidad de Warwick, en Reino Unido, un doctorado en la Universidad de Londres en Human Metabolic, en Nuclear Magnetic Resonance. Okay. El profesor Jimmy Bell ingresó a la universidad como lecturer y posteriormente profesor en la Universidad de Westminster en el 2014, donde creó el Centro de Investigación en Optimal Health. Y bueno, todo esto tiene un interés en investigación en obesidad, en factores que se determinan para una óptima salud y el aceleramiento en envejecimiento. Bueno, sin más voy a pedirle que por favor comencemos esta interesante plática. Thank you, Professor, for being with us. It's a pleasure that you are here. Thank you.
Buenos días. Voy a comenzar en español. Voy a comenzar agradeciendo a los organizadores del Foro de Salud y Bienestar, sobre todo el recibimiento que tuve ayer y hoy día, gracias a Silvia, que ha sido un placer estar con ella y discutir ciencia y la vida en México, que es increíble. Y aquí se acabó el español, and now I switch to English to actually do the presentation of my scientific forum. And what I want to do is tell you a bit about biobanks and why biobanks and our experience in the UK Biobank, which is one of the largest and most successful biobanks in the world. I forgot my, can I have the laser? So if we can go to the next slide, please. So the first I think the mantra in biobanks is that it has to benefit everyone. This is actually absolutely essential of biobank. And sometimes in science we tend to forget why we're doing things. We get involved in the actual scientific research without any impact in the general population. So I think one of the rationales for biobanks is that it benefits everyone. So when it comes to biomedical data, there are key things of why we want to actually want big. And these are, we can uncover trends, help make data-informed decisions, improve decision-making in the complex processes, improve services, improve operational efficiency, and of course, one of the main important things is it will eventually help with cost saving in the UK. In the case of the UK, is the NHS, the National Health Service, but in other places, of course, it's our community services. We go to the next one. And the key to any biobank is that we have to look at two aspects. One is the breadth of the biobank. So we know that the effect of the size we want to look at is directly related or inversely related to the sample size. So if you want to look at large effects, for example, the effect of diet on physical composition, then you need a small number of people to study. If we want to look at very low effects, for example, genetic effects on environmental or the exposomes, as we call it, then you need very large effects. Very large population. If we go to the next one, please. And then we need depth. So how many variables are we going to measure? And this is, again, is very important. Then you go from simple exposome measurement to very high quality measurement of both genetics and in-depth phenotypes. So it's that combination that we play with when it comes to biobanks. If we go to the next one, please. So there are different types of data analytics. that the descriptive analytics will just summarize the events or the variables that you're measuring. The use of diagnostic analytics to help understand the underlying causes of diseases. Predictive analytics, and this is quite important for biobanks, to actually predict future events, and then prescriptive analytics that will actually tell you how to treat a particular problem. So the challenge is that normal typical studies will be between 20 and 30 people. When we go to biobanks, we need scale changes, and then we're talking about biobanks that will be no less than 10,000 to 20,000. And then we have the UK biobank that's looking at 500,000 people, and then there's a Chinese biobank that are actually looking at 5 million people. The UK is just starting what's called Future Health, which is going to do about 2 million people, but with a reduced depth of measurements. If we go to the next one. And as I said, the UK biobank is one of the most successful biobanks in the world, and because it has the breadth and depth of measurements, of which here is a very broad view of what the UK biobank measures. But literally, they took 500,000 people and they measure everything they can think of. And we have the advantage in the UK that we have the National Health Service. Therefore, we have clinical record of every individual that participates in the UK biobank. So we can look at the history and the clinical history of their parents, themselves, and their children. And that's integrated within the UK biobank. If we go to the next one. So as I said, the UK biobank has 500,000 participants, women and men of the age of 40 upwards. I investigate a contribution of both genetic predisposition and the exposome disease environment in the development of non-inheritable disease. And one of the things that we had done, and which I participated actively, is that then we decided, out of these 500,000, we decided to scan with MRI and DEXA 100,000 of those participants. If we go to the next one. So basically what we're doing is transforming big data into biological insight for disease. And the interesting thing about the biobank is it has to develop lots of technology and lots of science to be able to convert data into biological insight into treatments. And that's why we have to develop and I'll show you some of the science that we have developed to extract the information from that data. We go to the next slide, please. So in the imaging, there are three sections that have been divided: the brain, the heart, and the rest. This is run mainly by the Oxford group. They are looking at all aspects of the brain, both functional and anatomical. And I can tell you they derive over 10,000 variables out of the brain. And then you can relate that to genetic and environmental factors. We go to the next slide. Similarly, they're doing that with the heart. And then next, which is what we do, is everything that is left. We go to the next one. Everything, everywhere, all at once. So we scan subjects from the neck down to the knee, and we measure every single component of the anatomy, from lungs, liver, adipose tissue, muscle composition, and some other variables that have been developed by using deep learning. And my colleague, Brandon Wisher, here in the audience, okay, you can ask him all about artificial intelligence and deep learning and how we have actually extracted all the information. Go to the next one, please. So what are the benefits of going large? We can do genetic studies. We can do polygenetic risk scores. We can do genetic heritability of diseases. We can do disease diagnosis, biomarkers, physiological traits, behavioral traits, and so forth. We can look at aging. We can look at temporal changes. We can look at population studies. And remember that the UK Biobank, these 500,000 are subjects that volunteer from the general public. So there's a range of diseases and conditions, as well as healthy people, within the UK Biobank. If we go to the next one, please. So one of the first challenges when you do a biobank is what do you do with the data? Okay, you collected millions of data points, millions of variables, you have to analyze it. And I'll show you what the challenges are for imaging, and then how we combine that with other aspects of genetics and the environment. If we go to the next one. So normally we'll get an image like this, and if we did manual annotation, so basically we segment it manually, one subject, it will take us on average about 27 days working full time. And Sylvia has been quite important in some of the work on this annotation that we've been doing. So if we wanted to do 100,000 subjects, it will take us about 7,500 years to actually annotate the data. If we calculate if we took every single radiographer or technician in Europe, it will take us about 7 years to actually do the whole work. But Brandon and his team, if we go, they created, if we go to the next one, sorry, created a fully automated MRI deep learning analysis pipeline that takes the images, put it through a pipeline, use the manual annotation to train the pipeline, and then we'll get deep learning methods. And then if you go to the next one, please, you can actually see that based on deep learning and cloud computing and enough money, you can actually do all 100,000 people in less than a day. So this is where deep learning comes into play. You take its scale, you train it, you accelerate the process of extracting the science, which we need to actually understand. We go to the next one, please. So why do we want to do this? Because if we were to use the standard measurements in population study like body mass index, BMI, it will not tell us the full story. And this is just a simple example. So we took some subjects with a normal BMI, 21, and here we got the image of the subjects. The blue color is the external fat, adipose tissue. The red color is the visceral fat, which is biologically very active, very important to measure. And you can see, although all these subjects have the same age, the same BMI, they have completely different amount of visceral fat. So BMI doesn't tell the full story. We need to understand and have in-depth phenotyping of subjects if we are to relate genetic factors and environmental factors in the development of disease, but also in the development of treatment of those conditions. And this is a condition that we call TOFI. You are thin outside and fat on the inside. And this is actually quite common. It's about 15% of the population in the UK actually have this condition of TOFI. If we go to the next slide, please. So with this precision phenotyping, we can redefine the metabolic risk. We know, for example, that people with type 2 diabetes is associated with high levels of visceral fat and liver fat, but people with coronary heart disease is associated with high visceral fat and low liver fat. We don't understand why we actually, in coronary heart disease, you actually see an association with high visceral fat, and you will expect high liver fat. Actually, high liver fat appears to be protective when it's come to coronary heart disease, contrary to all expectation. You don't have to take note. I'm going to leave a copy of this, and you can actually keep it. So, so you can listen to me fully, and don't waste time. And when it comes to metabolic health, we can actually define health in a different way. So we can define health as people who have, when it comes to fat, enough fat in their body, but low visceral fat, low liver fat, but very importantly, low levels of fat infiltration in their muscle. And this is quite an important variable because we tend to, we tend to measure adipose tissue, but we do not look at fat infiltration in the muscle. And I'll show you examples of that in a minute. But also, the genetics started to actually show something quite interesting that before we couldn't actually do. And that there are people that can actually put fat or weight on in a favorable manner. So what we call favorable adiposity. So here we got subjects that have the same amount of fat, they're the same age, but the distribution is completely different. So they have very elevated levels of body fat, but the distribution is completely different. So their visceral fat amount is the same. The amount of subcutaneous fat is increased, but when you come to look at the ratio of visceral fat to subcutaneous fat, they have what we call a favorable adiposity, and the same with liver fat. And the reason for this, we believe, is that some people have the ability to put weight on, and they can expand the number of adipocytes in their body. So basically, they have lots of adipocytes, and they fill in with fat, and that expand externally. The unfortunate of us, okay, don't have that ability, and all we do is we increase the size of those adipocytes. And when they get full, then that spills over, and the fat starts accumulating in places you don't want to, which is the visceral fat and the liver fat and the muscle. And what's interesting, if we go to the next one, when we look at, so this is basically what I just said. We have two types of phenotype. The favorable adiposity, where you got all the fat in the external area and none in the ectopic area, and the unfavorable adiposity, where you got fat both external and internal, but also lots of fat in the ectopic area like the liver, the heart, and the muscle. This person will end up with lots of the problem associated with obesity. This person appears to be protected from obesity just because of their genetic background. And if we go to the next one, please. When we looked at favorable adiposity frequency of the alleles in South Asians, these are people who live in the UK, but they are descended from India and Pakistan, and they tend to actually suffer from more prevalences of type 2 diabetes. We actually found that the alleles are less common in South Asian than in Europeans. So although they have the same allele, the frequency of those alleles are less common, okay, in the South Asian, therefore they get less protection when it comes to the development of type 2 diabetes. We go to the next one. And then we can go even deeper. We start looking, because we got the image, we can extract, as I said, all the information automatically. We start looking at the quality of that muscle. So it's not only the amount of muscle you have, but the quality of muscle. So here you can see actually the water image. It doesn't really matter, where you just see the muscle, the fat, and a combination. And you can see the subjects that in someone who is lean or very athletic, you have very little muscle infiltration. When you go to actually people with type 2 diabetes or obesity, you see lots of fat infiltration in the muscle. And when you look at the association between the quality of the muscle and conditions like type 2 diabetes and coronary heart disease, we see that there's a negative association between muscle quality and type 2 diabetes. Muscle quality is lower in women than in men. In sarcopenia, we see an association between reduced muscle volume. So in sarcopenia, it's the amount of muscle that is important, while in frailty, is the quality of the muscle, which is the important bit. So we have a condition where we can actually look not only at the amount of muscle, but the quality that will tell us different phenotypes and the relationship with the development of certain conditions. So you can look at the quality of muscle. There's some study known by our group, by other groups, that the quality of muscle can predict the likelihood of all the people to have falls and have, breakage of arms or legs in their falls. If you go to the next slide. One of the interesting things about the UK Biobank is sometimes you don't have to ask scientific questions. It just gives you answers to questions that you weren't looking for. And one of the things that we found is that, for example, age of the liver actually changes the amount of fat in the liver and the pancreas, and as well as iron. And you can actually see the changes in the pancreas that actually goes up both in males and females, but actually increases in the liver and then drops with age. And the same is actually the number of changes relate very much to your age and to your physical activity. So the more active you are, or rather the older you are, the more active you should be, because the more likely you end up with fatty liver and with problems. If you go to the next one, please. And we can go beyond the simple measurements. One of the postdocs in the group, Maria, have actually looking at morphometric analysis, and we can see that the shape of the organs can relate to the development and how chronic the condition is. And this is a whole field of research. I haven't got the time to go through this, but it's actually there for people who are interested in this sort of work. Go to the next one, please. So this is some work that Brandon did during the pandemic. We were all sort of at home trying to do some work, and the UK Biobank decided to rescan some of the volunteers who had been scanned 2 years previously, and then some of them had COVID, and I'll show you some of those research. But some of the healthy people who didn't get COVID, were scanned 2 years later. And I call this 2 years closer to death, because surprisingly, even after 2 years, you can see very significant changes in the quality of both muscle, in the amount of fat in the liver, in the amount of changes in some of your organs. Even 2 years, the accuracy of the measurements are such we can detect negative changes, but just simply by sedentary life. And this is one of the beauties of biobanks, that when you can do longitudinal changes with in-depth phenotyping, you can detect the trajectory of change. And then we can use models to predict what's going to happen in 5 years' time, 10 years' time, if you don't change your lifestyle. We can also predict where you're going to be if you do change your lifestyle. And I'll show you that in a minute. So, as I was saying, this was part of the COVID-19 study. We looked actually at subjects who didn't have COVID, people who got COVID, and we looked at the severity of that, how much time they spend in hospital, where they spend in hospital. And just to summarize, a study done by Nick and Brandon again, where we actually looked at every single organ in the abdomen, and we found that elevated visceral fat and liver fat and small, the psoas muscles is your core muscle. You know, when you go to a gym and the people say you have to get your core muscle working well, but if you can actually measure, it's actually a very good indicator for clinical outcome when it comes to surgery and chemotherapy, and also it's a very good marker for the amount of quality of muscle that you have. And we can see that elevated visceral fat, liver fat, and a small amount of psoas muscle was related to the severity of the disease. And our models predict that visceral fat was the most important contributing factor to disease severity, even better than age or BMI. And that comes directly from the biobank. Simply after 2 years, just because people have COVID, we could actually predict the severity and know who is going to be more severely affected by COVID. And I think, and this is all speculation, so don't quote me and don't tell anyone, I think this does not only relate to COVID-19, I think it's also related to most viral infections. Unfortunately, the UK Biobank hasn't measured a viral load in the subject, but it's something that we have been trying to push for. Go to the next one. So this is actually quite interesting, and it's an unexpected thing from imaging. Is that we now can measure the age of a person, the actual biological age rather than the chronicle age. So this work comes initially from the brain. There was been lots of work looking at brain aging using imaging, and then those in our group, but also people working with the heart, they decided to see whether they could actually look at the age, the physiological age of every subject in the UK Biobank. And the answer is yes, we can actually predict the physiological age. This is what I call the Dorian Gray syndrome. For those who are not familiar with Oscar Wilde, Dorian Gray was a very beautiful young man who had a painting done and he wished he never aged, so he has his wish realized, and then his painting was aging, but he always looked young. And this I say to people who spend lots of time in the gym, that actually look very young and beautiful, that they should be worried about the age of the organs, because they might look young, but internally they might not. Yeah, and as you can see in this work in the heart, and Brandon and Nick again have done similar work in other organs in the body, we can relate at the age of what's called the age gap, your chronological age with your physiological age. And you can be younger than your chronological age, or you can be older than your chronological age. And with the UK Biobank, we can see that aging of your heart increases with visceral fat, subcutaneous fat, and liver fat, with diabetes, with income, and with musculoskeletal health. So not only are these variables important, but also the socioeconomic variables can actually be measured in the impact of individual organs. And this is just the heart. The same is true, not the same variable, but the same is true through biobanks, that we can actually measure the impact of this. They didn't look at psychological thing. The data is there to be looked at. And if I should mention this, actually, I should have mentioned this at the beginning, that the UK Biobank gives access to anyone in the world to that data. All you have to do is to apply with a project. It doesn't have to be a mega powerful project. It has to be a scientific project that is valid, and you have to pay a small amount of money, and it will allow you to access the data. And you can start looking at both psychological, economic, socioeconomic, political effect on the aging process of different organs. If you go to the next slide. So reduce heart aging, again, quality of your muscle, lean tissue volume. So if you got good muscle, you end up with reduced heart, physical activity, oily fish, because we have all the intakes of these subjects, okay, and cereal intake. That, I got no idea why. Yeah. I can see the oily fish, but I'm not quite sure what they mean by cereal intake, because I eat sugar puffs. I eat just full of sugar. I doubt there is sugar puffs that actually save your heart. But I think what's actually important for this process is that the biobank allow you to start looking in depth at the relationship and then investigate it. What it's giving you is educated guess of where to put your effort, both for intervention, for social interventions, and also for scientific intervention to develop new methodology or new critical intervention to get the utmost out of those interventions. Go to the next slide, please. So once you have these image-derived phenotypes, you start doing association with health outcome. And because we have clinical data for all the subjects, then we can actually do the association over any of these measurements that we do. And it's not only the imaging measurements that you can associate, you can measure anything, because we have basically all the genetics and all the socioeconomical and all the anatomical and functional measurements of each subject. And we can actually relate this to the disease outcome and development. If you go to the next slide. And just to take one example, for example, liver fat is associated not only with type 2 diabetes, very strong association, but also with other chronic liver diseases and also other conditions that we weren't expecting. But it was not associated with alcohol intake. And it's actually, at the end, actually, I should have put it this. If we look at alcohol intake, and this is not to actually tell you that you should go and drink, you actually get a U-shape when it comes to liver fat. So I actually plotted that plot to show my children. I got two boys that like going to a pub. I wanted to show them, how bad it was to drink alcohol. And I was expecting a linear, the more alcohol you have, the more fat you end up in the liver. But we actually got a U-shape. So if you go and drink daily, then you're going to have lots of fat in the liver. If you go drink once a week, you have a bit less, but quite a lot. But when you go and you don't drink at all, you actually end up with lots of fat in the liver. So even if you just drink when you go to a wedding, like in my case, I don't like alcohol, I like Coca-Cola, okay? This is not another advertisement for Coca-Cola. Coca-Cola is bad for you, but you know, you have to do some bad things in your life. And that's the only bad thing I do. I think it's not so bad, I guess. And then you see that the people who didn't drink any alcohol end up with massive amount of fat in the liver. The people who were the most protected were the people who drank 1 or 2 glasses of wine, and this wine, not spirit and not beer, wine, once or twice a week. I'm not recommending that. I'm just showing you what the science is. My children said, we are going to a pub after watching that graph. But we go to the next slide, please. So the association of these IDPs, we can associate it with lifestyle of every subject, including income, how much tax people pay, which is related to, also the postcode of where you live. And this is actually quite important. And this is an American study now in the UK Biobank, where they can predict the BMI and the fat content of a person based on the postcode. 2 millimeters. Because lots of these impacts on non-inheritable diseases have to do with socioeconomic conditions. There's an underlying genetic factor. In my group, I collaborate with geneticists. We spend all the time arguing with them. So we have 2 camps, those who believe that 80% of the problems are genetics, and the other group where I am in, I think 80% is related to socioeconomic conditions. We'll meet somewhere along the line. But we have seen that the correlation are very strong between lifestyle and some of the conditions that we actually see that relate to diseases. If we go to the next slide. So measurement association with disease, I said liver volume is related to the to liver disease and cirrhosis, liver fat to type 2 diabetes, liver iron, type 2 diabetes and iron deficiency, kidney volumes to chronic diseases, and so forth. Everything from one single image done automatically, thanks to my colleague here, Brandon, okay, to be able to actually measure this. We go to the next slide. And then we can apply the genetics. And we found, simply by looking at some of these IDPs, 92 independent markers, okay, in the GWAS, okay, 11 of which were completely new, never seen before. Of interest both to geneticists, to people who want to do a development of technology, and also to the pharma companies who are interested to developing new treatments. We go on to the next slide, please. In the case of liver fat, we found 8 significant GWAS observations, some of them completely new in relation to the accumulation of liver fat. And these genes are actually modulating your environmental factor. And that, there's no doubt. They're not determinant, according to me, but they are modulators of that fat. If you go to the next slide, please. And we found novel genetic variants with central obesity linked to liver iron, and it's beginning to understand some of the mechanism underlying iron accumulation in the body. So the importance of how and where the iron is accumulated relates to the genetics. The amount relates to your environmental factors. Go to the next slide, please. And this, I'm about to finish. This is one of, again, Brandon's baby. It's because the power of biobanks is that we can actually create new technology. And we created this new technology. And we were very pleased with ourselves because we're going to have 100,000 people scan, measure everything on them, and then we're going to rescan them again in 5 years' time. But we're starting in about 2 years' time. We're going to rescan all of them. And we have longitudinal data. But Brandon said, you know, in the NHS, they got billions of images that after the clinicians actually done the diagnosis, they just get stored away or thrown out. He said, we could take those images, put in our pipeline, and extract all the information beyond what the radiologist measures. Simple. There's a wealth of information that the National Health Service in the UK, and I'm sure in Mexico, have stored away. And what is happening in the UK, and this is my political message, is that we're giving all that data to private companies. Why don't we, the scientists, use that data with the technology that we have developed, which now private companies to actually do exactly that. Enhance the quality of the patient, empower the patient through maximizing the amount of information that we get out of every test that we go to the subject. And then we can predict the trajectory, where they came from health, where they're gonna be in 10 years' time, where they're gonna be in 5 years' time or 10 years' time, if they change their lifestyle, or if we do intervention that can actually impact their life, their daily life. If you go, I'll do, and so this is what some of the work, I'm not gonna go, if you want to talk about this, talk to Brandon. Can you see I'm passing everything to Brandon? This is my job. My job is to present and get the people who do the work be presented. So taking images that were acquired in a hospital, and we are using our pipeline to extract exactly the same information that we extract from the UK Biobank. If you go to the next one, it's not a clinical, but I thought I have to put this. This is work done by Nick and Brandon again, an opportunistic IDP. We have Dixon, it doesn't matter what it is, it's an image from the neck to the knee. And Nick said, okay, look, we can see all the arteries, the vein, we can see the heart. It's not dedicated to the heart, but it's just a whole body. And he said, well, why don't we use our deep learning method to extract as much information as possible? So he extracted the heart, thanks to some of the annotation done by our colleagues, and some of the arteries and so forth. And we said, okay, is the measurements that we take out of the simple clinical image, non-clinical image, the same as you get from a specialized heart image? And the answer is yes. We don't get everything, but the ones that we do get are the same. But more interesting, most of the heart images will cover only this area. We cover all the veins. So we thought, can we look at abdominal aortic aneurysm? And the answer is, if you go to the next, is yes. We can actually detect, on these simple images, we can actually detect who's going to have an aneurysm. We have had propensity to aneurysm. You have millions of images like this, or similar to this, in your hospital. That could you apply this technique and predict who's going to have aneurysm before they have them. You don't have to re-scan people. You don't have to do anything. You have to talk to Brandon, creating more work for Brandon. Brandon, every time we go to conference, Brandon goes like, you're giving me more work. I go, yeah, it's good for you. We can actually predict aneurysm. This is the value of, I stress, the UK Biobank and all biobanks, is allow us to develop new technology that we can actually apply to non-biobank data. If we go to the next slide. So how can everybody benefit? I've given you one example. The other example, yeah, again, back to Brandon. Okay, Brandon usually given the talk and say Jimmy was sitting there at the time. No, seriously. So how can everybody benefit? It's that we have now developed algorithms and models that can be applied to any subject in the world who is at the age of 40 upwards. Caveats. The UK Biobank measures many things. And our models, we have a model that costs literally £10,000 per person. Has no value to anyone. So we said, okay, let's start diminishing the number of variables in each model to get to a point where we can have a model that predicts something quite accurately, but that some people could do it at home, or they could do it in any hospital. So if you go to the next slide. So we can predict with our predictive algorithm, yeah, the amount of fat in people's subcutaneous fat, visceral fat, the quality of the liver fat, the quality of the muscle, with very simple variable based on the UK Biobank. The second caveat, that this is mainly done on European subjects. So the UK has quite small, about 15% of the population is ethnic minority, mainly South Asians and Afro-Caribbeans. I think there are about 10 Latin Americans in the UK Biobank. This is an opportunity for Mexico, because I went to a conference, and it was quite interesting. There was someone from India, and it was about ethnicity and ethnic minorities and science. And he stood up and he said, one of the problems with science today and medicines today is we're spending too much money on ethnic minorities. And there was complete silence in the room. I mean, my God. He said, yes, because most of the money being spent today in medicine and research and science is spent on white Europeans who are a minority in the world. There are more Latin Americans than Europeans. From a market point of view, you need to create predictive algorithms that are specific for every ethnic group. The Chinese population overwhelms everything. We don't have predictive values for Chinese population, or South Asian for that matter. So the idea of creating a biobank that is specific for Latin America is actually quite important, both so we can utilize this. Maybe it doesn't have to be the size of the UK Biobank, but it could work with the UK Biobank, okay, to maximize the impact and utilize many of these tools that we have developed and accelerate the process of understanding whether some of these predictive algorithms are the same, which is great. If not, how can we actually modulate them that will fit to a specific population? This is the current members of the Research Center for Optimal Health. As Sylvia said, I work in the Research Center for Optimal Health. I'm the director. We're trying to understand what health is, rather than disease, to define health, and how we define it. And lots of the people, most of the work I presented here was done by Brandon, Nick, and Luis here, and some of our collaborators from industry, which I'll show next. These are all the groups that we work with around the world, and the biobank, of course, being quite key, and some very clever physicists, Calico and Perspectum, which are companies working on aging and liver diseases, looking at health and physical activity, and many other groups around. Thank you. I hope that covered what you wanted to hear.
Now we are ready for questions.
Thank you. It was a great talk, very interesting. I have a question. What was the most striking difference you found between women and men during aging? Something that you didn't expect, and it was like, oh, that's so unexpected.
That's a what is the most striking difference? I think it's a very difficult question to answer, because all the striking differences, for example, muscle quality, yeah, we find that the quality of muscle for women is less than men. But then when we take into consideration physical activity, then those differences disappear. So lots of the differences are related to lifestyle rather than anything else. I think the biggest difference is the distribution of fat, basically, that women tend to put fat around the hips and men around the tummy. around the hips are protective, around your tummy is very detrimental. Yeah. So that's why I said to people that God must be a woman because has sense of humor. You can have fat, but you are in the wrong place. There are no striking differences really when you actually unwrap the tissues. Yeah, things are either smaller, but functionally, you know, most of the liver, most of the organs are smaller, but when it comes to correlation with disease, they all correlate with disease. There are not that many differences. The impact of the genes are the same, are similar, but the sizes are bigger or larger depending on the size of the person. So that I would say, Brandon, do you reckon differences between men and women? Right. I couldn't tell you. We do tend to do all the analysis separately because when you send papers into a journal, they always say, oh, do a separate analysis. But there's very little difference when you actually take into consideration the... I don't know about the psychological part, okay, or the dietary part. Yeah, or social part of this, but because it's not something I study myself. Yeah.
Thank you.
Gracias. Thank you for your very interesting talk. I have a couple of questions. One is more from an applied point of view. Do you have an estimate of how every person involved in the study, every subject or voluntary cost in terms of pounds or some measure of the economic costs for, and I think this is a not growing curve, but in the contrary, it is a tendency to more people, more cheaper the analysis, I think. Is this correct? And the other question is, how is the, you mentioned you passed very quickly by that idea. You have some results from these studies on political attitudes the people have. I thought you mentioned that. Some studies have found that people with some special or particular immunological function have preferences, political preferences, very associated to fear, to social and political fear, and they tend to be on the right side. Do you found that kind of things?
Okay. I'll answer the first one. It's difficult to calculate the actual cost per subject. And yeah, first of all, you're absolutely right. The bigger the number of subjects, the cheaper it becomes. Okay. But what we have been doing to the subject is that increasing the number of measurements. So that I would say that at the moment, given that we are measuring so many things, one of the most expensive part, of course, is the imaging. But because we're doing it at scale, it costs us about $100 per subject. Yeah. So I would say that about $150, you can do most of the things that are being done because you're doing it at scale. But then people start doing different type of genomic studies, and then lots of the costs can be removed by collaboration, yeah, with industry. So the UK Biobank has this agreement, first of all, that everybody who does work on the UK Biobank have to return all the results, the raw data, all the analysis, and the software to the UK Biobank to make it public, so everybody can use it. That's the first thing. Second, if a private company, which are the companies that have done most of the genomics and the metabolomics, get involved, they have the same obligation. So they have to return all the results, yeah, for 500,000 people to the UK Biobank users to be used. The only thing that they get preference is that they get a few months leeway where they are the only people with the data. Yeah. But after that, yeah, they don't have intellectual property of that data or anything. After that, everybody can have access to that. And that works really well because some of this analysis for 500,000 people, it's huge. It's huge. Yeah. So that's the way that the UK Biobank has managed to actually attract the resources to cover some of the more costly part of the UK Power Bank. And the third thing is that benefactors, benefactors who actually come and they say, okay, I'm interested in this area, I'm going to give money to cover that area of the cost and so forth. So the real cost for each subject is probably, I would say about £500 or about $500 per person. But the UK Power Bank hasn't spent that amount of money on each person because lots of the resources that come from outside. And I'm sure you have benefactors here in Mexico. If you're going to have a biobank, you know, they love imaging, and you can tell them that you can measure the age of the organs, okay? And I say to my colleagues, you know, people can live without a brain and without a heart, but you can't live without a liver. So, you know, telling them new things about their lifestyles and what to do, you'll see that benefactors will come along and actually help, because the science is actually quite amazing, especially when it comes to aging and the aging process, which is going to be a massive social tsunami coming our way, especially in Europe. Okay, they're going to bankrupt the National Health Service. In answer to your questions, can we do that over coffee? Because you're filming me and I'm not going to say anything. Yeah, because I'm going to be quoted on there. I will tell you that one thing, that a funny story that I decided, and I'm going to mention this terrible word, Brexit, in this talk. I decided to plot amount of fat against, so we know how people voted in different localities in the UK. We have how much fat they have as a group in each locality. So I plotted fat against the percentage of people who voted Brexit. And I'm not going to tell you the straight line that there was. The correlation was 0.8. Yeah. So what can you conclude from that? Do fat people cause Brexit? Does Brexit cause obesity? Yeah. Wow. I don't know, I leave it. So there are lots of things that are quite controversial. So I created that graph, and someone saw it in a conference, and they said, you should publish it. And I said, no, I'm not going to publish it. Yeah, you're crazy. But you work for a newspaper, you publish it. And they go, you're crazy, we're not going to publish that because people stop buying our newspaper. And I said, well, why do you want me to publish something so I get persecuted? Yeah, given that they are a majority. So things don't get published that are politically delicate, yeah, for those reasons, because nobody wants to publish it. I might be light exaggerating, but when it came to obesity and Brexit, this was done by several groups and nobody published it in a scientific journal. So I can tell you the other stories, if you like, over coffee. Yeah.
Okay, we have just one question. Here, this side.
Thank you, Professor, for a nice presentation. I would like to know, which is the way that you take from create the algorithms to take the reliable data from the image? Which is the way that you create the algorithms?
This is the perfect time to say, talk to Brandon over coffee. No, I mean, I could go to a long explanation, but it'll take a long explanation, and Brandon can give you a better explanation than Chinese whispers by me. Yeah, but it was a process that, we had using convoluted neural networks and different deep learning methods to actually look at it. And we tested different methods until we came up with the one that gave the value. The one thing I have to say, which is true, that doesn't matter what method you use, is ground truth. Mm-hmm. The quality of rubbish in, rubbish out. And so we have very good ground truth, which allow us to do deep learning in very small number of subjects. And this is key, yeah? Because initially we thought we were going to have to annotate 1,000 subjects, yeah? But we now get away with about, 20, 50, and then we run it, create a model, retouch it, and then with 100 subjects, we got a perfect algorithm.
Thank you very much.
But Brandon will give you more details. Sorry, Brandon, seem to.
And how well is accepted those predictions and those diagnoses that you make by the clinical physicians? Is the clinical environment accepting well this? Because it's you can have lots of correlations and learning from a solid ground truth, but the clinicians, do they accept these results?
Okay, that's a very, very good question as well. Okay. I have worked with clinicians for a long time, and I know what it's like to work with clinicians, and the clinicians like their safe place, you know, the area of comfort, regardless of what the science is. This is what I've been doing for a long time. Why should I change? It works for me. And I think the way we have approached it is to say, look, you say you want to scan people, you get 100 patients. Let's say 20% of those, the scan was unnecessary. So you wasted, 20 scans. Our models, we predict that those 20 people don't need scanning. So you save yourself. And this is the way they start thinking, oh, so I can predict, okay, who not to scan, rather who to scan, who not to scan, is a way of entry. And then they start seeing the value of the model, where do you scan, how do you scan them? We can also start developing models to actually work on those areas. We, for example, just written a paper that to predict fatty liver, which is way superior to the one the clinicians use. And we published the paper, and like you say, people don't pay attention. Why? Because the clinicians are happy missing it. But when that prediction saves time and money and resources, then it becomes actually important. And from then on, the clinicians see the value of applying this. Then they start seeing the value of algorithm for their clinical practice. So again, Brandon and Nick are working with clinicians, okay, where, for example, in irritable bowel disease, okay, and trying to actually have better prediction and better imaging assessment of certain conditions. And they see the value. So they actually begin to say, okay, you can save us time, money, and effort. And also for the radiologists, this is not to replace the radiologists, but to actually say, look, here you go, all these images, this is the one you should be paying attention to. Rather than paying attention to all these images, this is the one that you should be paying attention to. From a very callous point of view, it means that they can go home earlier. From a commercial point of view, they can do more. From the patient point of view, it's less likely that they're going to miss problems outside what they were expecting to see. And that's the way, and I think that's why in hospital, I mean, my ideal, I was saying yesterday, my ideal would be the creation of digital twins. So every time someone walks into a hospital, they have a digital twin to which you superimpose all the data. The patient has the empowerment of having their data in a digital form. We have to thank Google and Ericsson and Apple because we all got mobile phones, which are quite powerful. People could have all their data in an avatar that can actually then be used in the community, because you can tell people, look, you got fatty liver. If you do this, this is what your liver is going to look like in real time. This is what you're going to look. You can accelerate the aging in virtual reality and just say to people, look, in 5 years' time, press a button, 5 years' time, this is what your liver is going to look like. This is what is going to happen to you. Not on an average, to you, the person. When they go to the hospital, that can be integrated in. And the doctor will actually know. They will be able to say this, the social workers, the community workers will be able to look at people's avatar or share their people's avatar, which will be personalized, and say, you need this. We have national day to reduce fatty liver. You can actually say, okay, all you people need to do this. You people need to do this. You need to do this. Okay? Because your avatar is actually telling you what to do. We are not utilizing the technology to empower the patients. We are only utilizing the technology to empower private company. You can see where I stand, by the way, when it comes to private company. I don't have a problem with private companies. I think you have to work with them, but I think academics should make more of an effort to take that technology and translate it through the clinics to the community and vice versa.
Okay, so thank you very much. So we are going to finish our session today now. So thank you very much, Professor Jimmy Bell, for
Thank you for inviting
the
me.
conference.
Gracias por la invitación.